Okay, ready to start? That's not what I want. It crashed, that's why. There's everything. Okay, so to those of you who signed up for the test on Monday or Tuesday, you should be getting emails with all the information. Don't forget to do that. Claim your reward. Okay. Thank you for doing that. And so we just finished up Taylor and Maclaurin series. We spent 3 days on that. And if you have further questions, don't hesitate to get with one of us, office hours, or make an appointment. We're going to just press on to the new topic here, which is something different from that. So we're going to start off with a little bit of review from the beginning of the semester and see. I can't get this. There we go. So I'm going to give you an example here. Return to talking about rate and accumulation here. So this situation here. This is a rate function. It's the rate of change of concrete being poured into a form. Okay, so concrete being poured into a form. It's the rate of change, and this is in minutes, right? So this is minutes is our horizontal axis unit, and then this would be meters cubed per minute. Okay, so a couple of initial questions, reviewing all the hard work that we did from the beginning of the semester. And so the first would be, could you come up with a rough sketch of the accumulation of concrete, the accumulation of volume of concrete based on this rate function? And then could you express that function that you tried to sketch? Okay, so take a couple minutes to do that. So first task is make a rough sketch of accumulation of concrete, and we'll call this total accumulation with an initial amount of 0. Okay, so there's an initial amount of concrete poured of 0, and we want to sketch total accumulation over here, our f function. And once you have that sketch, then we're asking the question, how could you represent that function? So we worked really hard on this in the first month, 2 months of class. So this is a good review exercise. Is there a question on the?
Is the max at 7?
What's that?
The max.
The max rate is around 8. Yeah, so the max rate is at about 8 minutes. Okay? So given the rate, sketch the total amount of concrete, and then express that function. Express that function that you tried to sketch. Okay? You're either making progress or you're getting help. Okay? Go.
So, since there's a max here, is the time.
Okay. Uh-huh. Okay, so since this rate is always positive, what does that mean for the accumulation of concrete? Is it always going to be positive? Well, in this case, yes, but that's not really what the rate positive tells us. What does the fact that the rate is positive tell us about the accumulation? It's going to keep going up the whole time, right? Even though the rate decreases, it's going to keep going up, right? Remember that? Why doesn't it work? It should be on right now. Let's see. I have no no idea where I'm graphing. Oh, it's just... All right, so let's. I'm going to need your help here. So let's go ahead to see that. We're going to need to write that equation. For some reason my file has changed at the last moment. So who was able to write the expression for the function? Yeah. Nope. No, so we got a product, right? So if you have a product, it's no. How are we going to express the accumulation? Bryce, did you get it?
Yeah, the integral of R of t dx.
Okay, you want the integral from? So meaning the limits, right? So what will the limits of our integral be if we're going to 0 to x, right?
R of t dx.
Right? It's going to be the integral of the rate function. And we need a different variable, right? Okay, so remember this is our open form accumulation function for that particular rate function. Okay, and so now we want to graph that. On the right side. Okay, and so then we get the graph. Lots of you had a graph that looked like this. That was good, right? So as the rate is increased, if the rate is positive, this thing will always increase. Okay, so what kind of form is that accumulation function written in? Remember? That's open. What about closed form for this function? So we spent a whole couple weeks learning to write these open form accumulation functions in closed form. What would that entail? Getting this function in closed form. Who remembers looking at this rate of change function? What would it mean to get this thing in closed form? Kellen, do you remember? All right, so t to the fourth, e to the minus t over 2, antiderivative. Remember what technique that would use? Okay. Undoing the product or chain? Product. What would this need to be for it to be undoing the chain rule? What would one small change we could make to this that would be undoing the chain rule? T up here. Yeah. This t. If this t were t to the fifth, then we could do undoing the chain rule, right? Remember that? But since we have just e to the t and t to the fourth, we need undoing the product rule. And undoing the product rule in this by hand would require what? What would it require then? How many times? 4, right? So 4 times, right? So remember t squared took two iterations through undoing the product rule. So this is going to take 4, right? This will take 4 times. So that's why we, in this case, we really like open form because we just write the open form and let the technology graph it for us, okay? All right, so who's got these and who doesn't? Let's pass these out. Okay, so now you're gonna turn to the side that looks like this. When you get one, keep it on the side that looks like this. That's the side we're working on. There's a couple that don't have a back. They should be two-sided. If you got one that's not two-sided, you got the wrong thing. Anyone got one that's not two-sided? Make sure you got one that's a two-sided sheet. Okay, so if you notice down below, there's an empty set of axis, or empty axis there below these two graphs that you see here. And so our goal here is to do something new that we haven't done before. And so rather than have the rate as a function of time and the accumulation as a function of time, what about creating a relationship between the rate of change of volume and the volume? So maybe there's a real world situation where the time element is less important and we just want it more kind of operating in the background. And so we're interested in what is the rate, not at a given time, but at a given volume of concrete. Maybe that's of interest to the construction crew. They're not going to be thinking about time, but they want to know like when the rate is the greatest or when the rate is decreasing based on how much they poured, right? As opposed to they've got a stopwatch and they're timing it, right? So this is what we want to do. So you're going to think about how could you create that graph? How could you create that relationship between now rate of change and amount poured or volume? So I put the volume on the horizontal axis. So that's meters cubed. Your horizontal axis is meters cubed. And what? That's your vertical axis on the right-hand graph is showing you meters cubed. And then your horizontal or your vertical axis on the graph you're going to create is then rate of change. So, given these two relationships, how could we get a sketch of this new one that tells us what the rate of change of concrete is for a given amount of volume poured? So you're going to brainstorm with people around you, think about that, and if you have a good strategy, then you could maybe start working at it. Okay? Sketching rate of change as a function of now volume, given the two relationships that we have. Okay, go. Okay, so who has a strategy they think is getting them going in the right direction? Yeah, Caden.
I related them using time, so I look at both graphs at the 5-second point.
Okay.
And so like the accumulation at 5 seconds is around 100. Like graph 100 on the x-axis, and then the rate at 5 seconds is approximately 40. So I graph the y coordinates 40.
Anyone else come up with that strategy? He said pick a time, get the volume at that time, get the rate at that time, and that gives you a correspondence point of time and rate. Lots of people. Good. Okay, so he said at 5, you said it was about, the volume was about what? 100. So we're looking at, so for time 5, we're looking at volume of 100, and you said the rate was about? So does that give a something like that? What's that? Which is 50?
The value of the rate.
Okay. So at 5, we agree on 100 for the, about 100 for the volume, but more like 50? So this isn't exact, but it's the idea that we get a volume of 100 and a corresponding rate of 50, and that gives us one correspondence point on this in this new relationship that we were trying to build. Okay? What could you do next? Yes. Okay, go for it. Tell me.
I chose like 7.
At 7? Okay.
So I said it was about 200 for the volume.
Okay.
Around 70 for the rate of change.
So she said at 7 minutes we get about 200 for the volume and about, what was it?
70.
70. Now these are just estimates, but that's all we care about right now. So those are not exact, but we're just from picking off the graph. So do you see that we could generate lots and lots of correspondence points this way? Pick a time, and that will give us a volume and a corresponding rate. And then we could plot that point, and then put all the points together, and we get what we want, right? There we go. Okay. So watch. So this is exactly what you guys said. So the t equals 5. Here we go. T equals 5. Ready? So the value of t is the same on both of those horizontal axes. And so we got a value there for the rate and a corresponding value of the volume. Where's the volume go? Volume's going to go on the horizontal axis of our new graph, and that corresponding rate will go as the vertical coordinate, giving us a point for t equals 5. Okay? And you guys chose the same exact ones as the video. Nice job. So t equals 7. Rate, volume. Volume goes on the horizontal axis. Rate goes on vertical. Gives us another point. And so we can keep doing that. Here's t equals 9. T equals 11. So we get the idea. Each time we'll generate a correspondence point of volume and rate. And then we can plot that point. Okay, so here's a table. It's set up as a table showing lots of points there. And so now we get a feel for the whole relationship, right? When we see lots of example correspondence points, we get a feel for the whole relationship, and then we can see how that's varied continuously in this one. So watch, ready? Now, I'll just play this and see what we're looking at there. So down here, what is f of t, the x-axis coordinate there, the horizontal coordinate? Where does that come from? And where do we get volume from? So just focusing on the volume. Where is that coming from? That horizontal coordinate of our new graph. It's coming from where? Right, the y value of the right-hand graph up there, right? The y value of the right-hand graph is giving us those values, and then the y value of our new graph comes from? Red and red, right? The rate now coming from the rate or the vertical coordinate on the left graph. Just watch it one more time. So they're color coordinated. So you got blue coming from the blue function value on the right, and then the red coming from the red function value on the left. Okay, so what this new relationship is an example of what we call a, I can't write because I'm in the wrong. This new relationship here is called a parametric function. And that's what we're going to be working on the next week or so, parametric functions. So parametric functions are functions that are based on a parameter which is kind of a behind-the-scenes variable. Okay? So the parameter in this case, what's the parameter that's behind the scenes generating these ordered pairs? What quantity is behind the scenes generating those correspondence points for that graph? What was it? Time, right? Time in minutes. So the parameter is our independent variable in these functions. But it doesn't get graphed. It doesn't end up as a coordinate on the graph. What gets graphed is our correspondence points. So we get our x value of the correspondence points are some function of t, and the y values are some other function of t. But we still graph correspondence points of x and y, not t. So the parameter in this case was the independent variable, and that was t. And then our dependent thing then is no longer a single value, but it's an ordered pair. So our dependent output of these functions is now a correspondence point. It's both an x and a y. So our dependent, I'll write quantity, but it's really two quantities, right? So the independent quantity is in this case, it's time. It's this quantity t that's kind of operating behind the scenes. It's that t is generating then two values, x and y, or vertical, what we put on the vertical and horizontal axis. And that's our dependent now. Our dependent is actually now an ordered pair, just not just a single quantity. Yeah, Nick?
Your selection of which was x and which was y in this ordered pair is arbitrary, right? They could have been flipped the other way.
Exactly. So that would have been a different function if we would have been charting volume as a function of rate. Right. So that would be a different parametric function, but the same idea. Yeah. So you choose, right? Yeah.
Isn't this essentially like just finding r sub f of the inverse of f of t?
Okay, yeah, so exactly, right. So he's thinking if you did the inverse of f, that would be what, time as a function of volume. And then you could put that time as a function of volume into the rate, and you'd be getting rate as a function of volume, yeah.
Then the independent variable would be the volume.
Right, and that
In that composition of functions.
right, but so in that in doing it as a composition of functions, it wouldn't be a parametric function. It would be it'd be a composition. So what he's saying is we could do r sub f of f inverse. Is this right? What's that? It's okay. So, well, it would be the same. It would be the same function. So he's saying that if you do the inverse of this function, you would have time as a function of volume. So your initial input would be volume. The inverse function would give you time, and then you could take that time and put it in this and get rate. And so you'd still have the same starting point and ending point. You'd still be starting with volume, and your inverse function would give you time, and then this function would give you rate of change of volume.
So he's just finding a different way of writing a function.
It's
With the same result,
So it's a kind of a different perspective on the same thing. That's the perspective of a composition where the independent value is volume and the dependent variable is rate. Okay, So that's different than a parametric function, because in a parametric function, our independent variable is going to be time, and our dependent quantity is going to be a volume and a time. Does that make sense? So it's kind of two different perspectives on the same situation. This is a single function that says a composition. This is a single parametric function given a time. It gives us ordered pairs or correspondence points of volume and rate. Okay, so let's talk about graphing these things in GC. So what did we say? So we said that the okay, so now I've got my independent variable here as t. So I'm going to go from 0 to t, and then I need some new variable in here. Say u. Okay, so what do I want to do? I want to graph this relationship, the one we just found, as a parametric function. And so in GC, if you do control 2, remember control 2 gave us points, right? So that's essentially what a parametric function is. It's gonna graph a set of points. So we use our control 2 that gets us a point, and then we say equals control 2 again. And what does x equal here in this relationship? He wants f of t. Agree with that? What did we put on the horizontal axis? Volume, right? So yeah. So for x, I'm going to put f of t. Okay, and then we want the y coordinates to be r sub f. Makes sense, right? So we're just going to graph the set of all points whose horizontal coordinate is the volume, f of t, and whose vertical is the rate.
Mark, when you're doing this, are we not supposed to use x as an independent variable while defining functions initially? Will it conflict with the parametric?
No. So when you're defining function, you can use any variable you want, and it's just a dummy variable. It doesn't think of that as the x-axis when you're defining a function. But in any other statement where you put x, that will invoke using the x-axis. But in a function definition, any symbol you want. So I could put y's in here, y and y. I could use all u's, x's. Doesn't matter. Yeah. But now here, this is definitely talking about when I say I'm going to plot a point x, y. Now this is saying this is going to be the x value of my point, and this is going to be the y value of my point. All right. So let's do blue. Okay, and so now when I graph that, all right, so I don't know, anyway. So yeah, so why is it showing such a small part of the graph, which just should have just appeared? It did every time when I got ready for the class. It just appeared, but now it didn't. Anyway, so why is it showing? So now I'm only showing, say, from 0.2 meters cubed and 0.5 rate of change. So what's happening here? Well, if you look over here, t is only varying from 0 to 1. This shows you what values of t that you're varying between. So what does that mean for us? In our example, if we're varying t from 0 to 1, we're just looking at what? What are we looking at? Just 1 minute, right? And how many minutes was there on these original graphs? So how can I then make it show what I want it to show? I want to vary t from what? 0 to 30. So if I vary t from 0 to 30, that should generate all the correspondence points I want. Okay, now suppose that I'm graphing several parametric functions, and they all want a different range of t, but I want to see them all at the same time. So what's convenient is I do want to have that at 0 to 1, so I have a kind of a universal, easy range of t, But I want to be able to see, I still want to be able to see my whole graph here. What can I do? How can I, with t from 0 to 1, how can we see that whole graph that I just showed you when I had t from 0 to 30? So now t to 0 to 1, you can't see anything, right? Because there's just this teeny little blue speck here that's not showing up. So rather than change what's a different way to show the whole thing, rather than changing the range of t, how could I, yeah, so how could I scale, what could I do here in the points that I'm plotting to show all values? So in other words, as t goes from 0 to 1, I want these arguments to go from what to what? I want the arguments of my functions, f and r sub f, to go from what to what? Right. So as t goes from 0 to 1, I want those, what's inside the independent argument there, to range from 0 to 30. How can I achieve that? 30t. What if I put 30t in there? Would that do it? So now as t goes from 0 to 1, when t is 0, I'll have f of 0, and when t is 1, I'll have f of 30. Same with the rates. That should do it, right? So is it a different function or the same function? So I'll write the one I had before. So here's the original one we had, and now the new one has changed those arguments from t to 30t. Are these the same function, same parametric function, or different parametric functions?
I think it's the same. You did the same thing.
What's that?
Because you multiplied both by 30.
So same. Anyone think they're different? So we know that if we take this one as t goes from 0 to 1, we're going to get the whole graph, right? But on this one, we need t from, and when I take this one from t from 0 to 30 and this one from t to 0 to 1, do I get the same set of points or a different set of points? Same set of points. So are they the same function? Okay, so that's something we're going to explore more. We do definitely get the same set of points, but are they the same function? Do you get the same correspondence point for the same input value? No, right? So it's a different way. This generates all the points in a different way for different values of t. And we know that functions are a relationship between your independent quantity and your dependent quantity, right? So if I put 0.5 in for this one, what correspondence point do I get? F of 15 and R sub f of 15. And if I put 0.5 into this one down here, what correspondence point do I get? F of. So for this reason, they're different functions. They generate the same set of ordered pairs, the same correspondence points of volume and rate, as long as you get the right range of t. But they're different functions because you get a different correspondence point for the same value of t. Okay, so let's try something different here. So if you want to flip over your sheet, and the first thing I want to have you correct is a typo. On that top graph on the right, it says distance from Casa Grande. And that should say distance from Maricopa. So let's just get that straight before we think about this here. So this right here, right there, change that to distance from Maricopa. That should say Maricopa right there. Okay, now let's read. So driving from Tucson to Tempe, heading northwest, Jacob comes to a straight stretch of highway shown. The final goal of this activity is to make a sketch of Jacob's distance from Maricopa as it covaries with his distance from Casa Grande. So the bottom graph here, this. So this is the one. This is the graph we're after. Okay, Jacob's distance from Casa Grande as in relationship to distance from Maricopa. So that's our final goal. So to accomplish this, and that just trying to do that directly is a difficult task. It's very difficult. So there's this intermediate step that's very, very helpful in accomplishing that. So that is to sketch two individual graphs, one for Jacob's distance from Maricopa and one for his distance from Casa Grande. But in order to do that, I'm not telling you what the parameter is. So this is the idea of the idea that we're building a parametric function, but I'm not telling you what the parameter is. So like we had before with the concrete example, this was minutes on both horizontal axes, right? They were both minutes. In this case, the hint I'll give you is it's not a time quantity. It's not a time quantity, but there's this common quantity in this situation that's very helpful to be our parameter, for which you can mark off Jacob's distance from Casa Grande as a function of that mystery parameter, and his distance from Maricopa as a function of that mystery parameter. So the first task is to kind of brainstorm and think about what would this kind of common, or like we say, behind the scenes quantity that's going to be really helpful to build these two in order to then, once we have these two relationships, build the final goal is the relationship between his two distances from the two different cities. Okay, so let's take just a minute to think of.
It's a straight section.
Yeah. So think about building these graphs. Your distance from Casa Grande. So is that what you want? You want rate to be the parameter? Is that what you're saying? What's that? So that would be then you'd have an increasing rate. So this would be like an increasing rate. Is that what you want?
This is true. He would just eventually have to be going like 500 miles per hour.
Yeah. So and then you'd have to be tracking his distance as his rate is speeding up. I think that's the wrong way to go. Okay. Any ideas? So what might be this parameter that's going to make these graphs very manageable and help us to achieve the final goal? Okay, so she's saying total distance down the road. Displacement from starting point or distance down the road. Other people came up with that? Okay, good. Yeah, so that is going to make this very manageable. So what we can do is we can look at kind of increments, right? So look at kind of equal amounts of distance to make this, to look at, generate some ordered pairs for both graphs. And then you can track his distance from Casa Grande as a function of how far he's traveled down the road, and the distance from Maricopa as a function of how far he's traveled down the road. And you can covary those. And once we have those two graphs, we can use those two the same way that we use the volume and the rate of the concrete to form the relationship between his distance to Maricopa and his distance to Casa Grande. So can we sketch these two graphs? These two graphs now. So we said our parameter is going to be, so let's say distance traveled from this starting point, right? So this is like the starting point here. And so distance traveled down the road, displacement from starting point. And then once you have those two and you can confirm that with people around you, then you can start trying to build the graph below. Okay, go for it.